Well, hello everybody. Welcome to another episode of Master the NEC, where we talk about the National Electrical Code. My name is Paul, and welcome to the show. Today's show is sponsored by myceudepot.com. That's myceudepot.com for all of your continuing education needs in engineering, PDH credits, OSHA credits, whatever type of continuing education, electrical exam prep, plumbing exam prep, mechanical exam prep, whatever you need are available at myceudepot.com. You can also get there from our website, as always, masterthenec.com. Thank you for their sponsorship of the show today. Now, today's show, we're going to talk multifamily dwelling load calculations. So, there's a standard method and there's an optional method. On today's show, we're going to talk about the standard method because standard method is not used as often as the optional. The optional usually results in a smaller service, conductor sizes, and a smaller overall service. But for exams, most of the time, you're going to get the standard method. That's the one they're going to throw out to you. So we'll have videos and audio podcasts on both. But today, we're going to do the standard method for dwelling calculations. Now, a couple things up front. Sometimes people get real intimidated when they hear that it's a multifamily dwelling calculation. I'm here to tell you that the multifamily dwelling calculation is no different than a single family calculation for a dwelling. The only difference is the number of units. That's the real difference. And that does come into play. When you got to do whatever your value is times the number of units, it's just going to multiply whatever the value is by the number of units. Whereas if it's a single family dwelling, it's only one unit to contend with. Well, if you have a condominium, let's say with 18 units, which is the actual topic of today's show, then you're going to take whatever your value that you would do, say, as a single family dwelling, and you're just going to do that times 18 because there's 18 units and they're all identical. Okay? So don't let it complicate it. And don't let it confuse you because it really doesn't need to confuse you. So when you go to take an exam, the exam's got to give you the variables. And if they want you to do the calculation, they're going to have to give you what they need. So a lot of times when I'm doing these podcasts, I tell people that you always can pause the audio at any time, get your code book, and then hit play again and catch up and read the code and then put pause again. That way you can kind of listen and follow along because I tend to try to paint you a mental picture of what I'm going through here in a podcast. And I'm known for doing that, and hopefully I'm able to convey that because I don't always like to do videos. I love podcasts. So because you're able to listen to a car when you're in the car, and then when you get home you can play it back and pause it and work it out on a worksheet or whatnot. It just makes it real convenient for you. So I'm going to give you the examples today, and I'm going to do it really slow so that you can pause and write down each component here on a piece of paper so that you can do this calculation with me. And that way you kind of learn how to size it. Now, today's example we're going to keep pretty simple, obviously because it is a podcast. We're going to deal with a condominium that has 18 of them. Okay, there's 18 condominiums, units, dwelling units in the condominium. The service voltage is simple 12240 volts, okay, keeping it very simple, single phase, obviously. And what we're going to do is we're going to calculate the service and the neutral that's needed for these units. Now, so while to many people that sounds like a daunting task to do in a podcast, we really are going to try to cover it to the point where you really get it, all right? So now, there's a certain number of steps that we like to follow, and I'm going to kind of take you through the process. I will tell you that Article 220 and Part 3 for the standard calculation is designed in a pretty logical format. If you simply just go down each section, it's pretty easy to follow along. But we'll kind of give you the heads up on how you do it. And also I will say, watch for a video that will come out with all of this, as well as I work on new graphics and all to have in the video for calculations as part of the calculation series. But I really just wanted to walk you through this. So let's talk about what each one of these condominium dwelling units actually has. Now, we're going to talk about how much floor area. So each one of these condominiums has 1,000 square feet. Okay, So each one of them has 1,000 square feet of floor area. So you're going to write that down. Each one of these units also has a water heater that has a 1.5 kW, okay, or 1.5 kilowatts, or just 1.5 kW, and it's a 240 volt appliance, and it is a fixed appliance, obviously. The next thing we have is a 3 horsepower air conditioner at 240 volts. And of course, since it says 3 horsepower, you're going to have to find out what the actual amperage is of that by going to 430.248 and find out what that is, because it is a single phase. The next thing that we have is a 4.5 kW heating unit. Okay, so you're going to compare the larger between the AC and the heat. So in this case, we have a 4.5 kW heater component, and that is 240 volts, so you want to write that down. Each unit also has an 8 kW electric range. Okay, so every one of these 18 units, dwelling units, have an 8 kW range, and they are a 120 to 40 volt range. The next element that all of these dwelling units have is a 4.5 kW electric dryer. And it is a 120 to 40 volt dryer. The reason I'm telling you the 120 to 40 volts is because we are going to calculate neutral conductor sizes, or the load that's going to be on the neutral conductor. So you need to take that into consideration. And lastly, every unit that has obviously air conditioning or heat has an air handler. And so the motor that's in this air handler is our largest motor, and is a 0.5 horsepower air handler at 120 volts. Okay, so that is the largest motor. So I want to throw that out there. Now, if you're taking an exam, they will give you these elements, okay? Especially if they want you to take them into consideration. They're going to give you these elements, okay? So I have given you, let's see here, 1, 2, 3, 4, 5, 6, 7 elements that you need to have taken into account and put down. Now, at any time you can pause, go back and make sure you have those 7 elements. But of course, we're going to go over each one of them as we move through part 3 of Article 220 in order to calculate this multifamily dwelling load calculation. But I have given you each one of these elements. Okay. First thing is first, I'm also going to get my NEC going here so that we can kind of work through this together. And I'm going to kind of give you the steps that I follow when I'm doing this calculation. All right, now, first things first, step 1. I need to determine my general lighting and receptacle loads, because I've got 3 little things to do here, 3 little steps that I'm going to do that I'm going to have to apply some actual general lighting and receptacle demand factors to, and it's a good thing, okay, for diversification. I got some demands that I'm going to be able to place here. But I have to come up with the values to be able to apply these demands to for the general lighting and receptacle loads that are allowed in 220.12. So, first things first, I'm going to use 220.12, the table. Now, 220.12, the table, is a table that tells me what my general lighting loads by occupancy are. And since we're dealing with dwelling units, you'll notice that in this table, it says that you use 3 VA per square foot. So now we said we had 1,000 square foot facility, so obviously it's 3 VA per square foot. Okay, so that's what's in table 220.12. So that's where we kind of start first when we're going down this path. We want to do these things first. So that's kind of step 1. So we take the 1,000 times 3 VA equals 3,000 VA for that individual unit. And of course now we've got 18 units. So now we're going to take that 3,000 times 18. And that equals 54,000. Now remember, if it was a single family dwelling, we wouldn't do it times 18. We would be done at the 3,000. Okay? But we're doing the service for this entire condominium. Okay? So we have 54,000. So you're going to write that down. In other words, create me 2 columns now on your paper. We have a service column and we have a neutral column. Okay, so now we're adding up the things that are in the service sizing column. Okay, so that's the first thing. Next, We know that the standard also requires in 220.52b, now in A, is that we need to have small appliance branch circuits and we have to have the laundry branch circuit. Now, in our equation here, there was no laundry facility on this condominium property. If there was, then I would be able to omit the laundry application. Okay, but in this case, we didn't mention that. So that means every one of these units has to have a laundry circuit, right? So to see how that works out, you're going to go to 220.52a for the dwelling units, and you'll see that we're going to deal with the small appliance circuit loads first. Now, these are the small appliance circuits that are required by 210.11c1, and there was no less than 2 of them have to apply here. And when we're doing a calculation like this, it's 1,500 VA each. Now, what happens if I were to have a big house and I had 5 small appliance branch circuits in it? Then I'm going to have 1,500 for each one of those 5. But in this case, it's only 1,000 square foot. We didn't say anything otherwise, so we know the code minimum by 210.11c1 is I got to have at least 2 small appliance branch circuits. Okay, and in that case, it says here in 220.52a that they are 1,500 VA apiece. Okay, so in my case here, I've got 2 of them, so it's 2 times 1,500 times, remember we have 18 units here. So it's 2 times 1,500, which is 3,000, times 18, which is 54,000 VA as well. So I've got 54,000 for the 3 VA per square foot value for 18 units. Now for my small appliance, I've got 3,000, which is the 2 1,500s, because I have to have at least 2, times 18, which is 54,000. So I've got 54,000 and 54,000. I should write that down. Now, the next thing I'm dealing with is 220.52b. And you notice how it just follows down the code? It's pretty simple once you understand the concept. Now, this says the laundry circuit load. Now, the laundry circuit is required by 210.11c2 unless any of the exceptions apply. Now, those exceptions, again, is if the laundry facilities are already on site, and then that would be calculated for the house load for a house panel. We don't have that equation here. So in this case, the laundry circuit does apply. And the code says right here in 220.52b that you're going to take 1,500 VA, okay, for each 2-wire laundry branch circuit installed as covered by 210.11c2, okay? Now, it does tell us that this can be considered into the general lighting load, and we're already doing that because that's what we're doing right now. We're adding up all the general lighting loads together right here, and this happens to be really a receptacle load, but you can see that it's an actual load, so it's getting added into this value that we're going to add all together here. So, laundry load, at least 1. If there was more than 1 laundry circuit, and I wouldn't imagine so in a 1,000 square foot unit, but if there was, it would be 1,500 for each. But in our case, it doesn't say anything about that. If you're taking an exam and it doesn't say anything about a separate laundry facility, then you want to make sure if you're dealing with a multifamily application that you add this laundry circuit in here, 1,500 VA. Okay, so it would be 1,500 VA times how many units? We have 18 of them, so it's 1,500 times 18 of them. That equates to 27,000 VA. So at this point, I have 54,000 for the 2 small appliances times 18 of them units. And then I got the laundry circuit, 1,500 times 18 equals 27,000. So 54,000, and 27,000 equals 135,000 VA. Okay, so that was step 1. Step 2, kind of in step 2 covered appliances and laundry. Now, and the square footage, you added them all together. Now comes step 3. Now, step 3 is telling us, okay, now I am allowed to apply what's called a demand factor. Now, this demand factor gets applied, and you'll also notice that it states that as well, at the end of 220.52a and b, it says in the last paragraph, it says shall be subject to the demand factors provided in table 220.42. It says that after all of them, okay, in this application. It says that after 220.12, it makes that reference, and it makes that reference after 220.52a, 220b, so that's why we're using it. So now let's go look at the table for the demand factors in 220.42. Lighting load demand factors. And again, this is including our general lighting and receptacle load. That's the general receptacles, you know, that you're going to space every 6 feet and 12 feet so that no point along the floor line is more than 6 feet from a receptacle. That's what's required in 210.52. All of those normal receptacles, all of that type of thing, all the general lighting. We're not talking about specialty lighting. We're talking about the general lighting application. All of that gets figured in here and applied to this demand factor. Now, if you look at table 220.42, you'll see that it deals with the types of occupancies, and then it deals with the lighting load in which demand factors actually apply, or that portion of it, of the value that we already calculated here. And of course, then you get your percentages and demand factors that you can apply. So let's look at it. So we took the 54,000 plus the 54,000 plus the 27,000, gave us 135,000 VA. Now it says here in table 220.42 that for dwelling units, I take that first 3,000 at 100%. Okay, so I take the 135 minus 3,000 times 100%, which is obviously 3,000. So that 3,000, I write that down. That is 100%. I take the 3,000 at 100%. Now, when I took the 135 and I minus that 3,000 at 100% from it, that left me with 132,000. Okay. Now, remember what it says here. It says from 3,001 to 120, it's at 35. So in our example, once we got the next value, which is the 132,000, then from the 3,000 to the 120 is 117,000. So we're able to take that value at 35%, because that's what it says here. We took the first 3,000 at 100, and then from 3,000 all the way up to 120, which is 117,000 between 3,000 and 120, we can take that at 35%. So 35% of our 117,000 is 40,950 VA. So we write that down. So we have a 3,000, then we have a 40,950. Now, once we get over the 120, then we've got to go all the way up to our 135. Okay, so that's going to be the difference of 15,000. So that remaining 15,000 that's between 120 and 135, that 15,000 we're able to take at 25%. That's huge. Okay, so we only need you get to take 25% of that. So 25% of 15,000 is 3,750. So now we're going to add all three of those values up. So it's 3,000 plus 40,950 plus 3,750 for a total of 47,700 VA. All right, now that is our general lighting load. We write that down. That's the first part of our equation. We went through it step by step. That's the load that we're going to go over here to our service column now. And the first one we're going to write down is the general lighting and receptacle service column. We're going to put 47,700. Now, right beside it in the neutral column, we're going to write 47,700 as well, because these are 120 volt loads. So there is neutral current here. So both are going to be the same. Okay? Now, the next thing we're going to move on to, and it's logically how you follow part 3 and when you're doing this, is once you move down, the next thing you're going to look at is appliance load. Now, what appliances do we have? Now, you might have more when you're dealing with, say, a regular dwelling unit. You might have 4 or more appliances, and you can apply 70% demand factor to them. Well, in this case, since we have 18 units, but we only have one appliance, which is the water heater, we can still apply it as more than 4. So in that case, we're going to use a 75% demand factor because we're allowed to do that. and that's allowed to be done in 220.53. So in our case here, we had a water heater which was 4,500 VA, or 4.5 kW, and they equate to the same. Then what we have is we'll take the 45,000 times 75% times how many units do we have? We have 18 of them. So we do it times 18. So that gives us 60,750. Now, we're going to write that right underneath the general lighting and receptacle under the service column that we just put the 47,700 in. We're going to write 60,750. Now, right next to it in the neutral column, we're going to put 0 because these were 240 volt loads. There is no neutral. So we put nothing there. Next thing, we're simply following down the items here, the applications, the articles in the code book here. The next thing it says, we're going to deal with the electric clothes dryer. Well, we also said that electric clothes dryer in this unit was 4.5 kW. It was a 120, 240 volt load, so we obviously know there's going to be a value in both the neutral and the service column. However, let's kind of stop here for a second and look at this. Now, since we're dealing with the clothes dryer, you have to really look at what it says in 220.54. In 220.54, it says the load for household electric clothes dryers in a dwelling unit shall be either 5,000 watts, okay, or VA, 5,000 VA or 5,000 watts. They work simultaneously here. It doesn't matter. VA or KVA or KW all can be considered equivalent here and whatnot. So 5,000 watts would be equivalent to 5 kW, or it would be 5 VA, 5 kVA, which would be 5,000 VA, or whatnot. I think you get the point. All right, so it says that the load for a household electric clothes dryer in a dwelling unit shall be either 5,000 watts of VA or the nameplate rating, whichever is larger for each dryer served. Well, our dryer was 4.5 kW, but it says right here that we have to use 5,000 because it is larger than the 4.5. Now, if this was the optional method, we would just simply take the nameplate, and that's why the optional method can be a little simpler to do. But here we have to remember that we got to take 5,000 VA in our equation because that's what it says we have to do in 220.54. Now, good news. We got some good news here. When we're doing the dryer, we're going to also be able to apply a demand factor because we get to add the total because we're doing a service calculation here. We're not doing the individual unit here. We're technically doing it for service for 18 units. Okay, so we're trying to do the service for this entire condominium. So we're going to take 5,000 times 18. But now we have to find out what the demand factor that we can apply for the 18 ranges. Now, how do you do that? Well, you notice that it says in 220.54 that you're going to actually go use the demand factors in table 220.54 shall be permitted. Okay? So, obviously we want to use them because the demand factor is going to result in a smaller service, less value. So it says we're permitted to do it, so we're going to do it. So, if you go look at table 220.54, you'll notice that it has a number of dryers. Now, we're going to come down. Now, you notice that we fall between the column that says 12 to 23. Now, the demand factor says 41% minus 1% for each dryer exceeding 11. Well, we have 18 of them. So, 18 minus 11 is 7. So, since it's 47%, we're going to take away 1% for that 7 that exceeds 11. So, that means it's 40%. So that's our demand factor. So it's 47% minus 1 for every dryer that we exceed 11, and we exceeded 11 by 7. You get where we're at now. So basically that's 7%. So we take 7% away from the 47% baseline, and that means that it's 40%. So when we go back to our calculation, we're going to do 5 kW times 18, because there's 18 of them, times 40%, because that is the demand factor we're allowed to apply in accordance with table 220.54. Then that's going to result in 36,000 VA. Okay, so that's the value you're going to write underneath your 60,750 that you just wrote for the water heater. So you're going to write 36,000. Now, we have a neutral load here because we said that this dryer was a 120 to 40 volt dryer. So what do we do with the neutral load? Well, now you want to look at 220.61. Now 220.61 is how we deal with the neutral application. Now 220.61 B is going to tell us what we do here. And it says that the permitted reduction, it says a service or feeder supplying the following loads shall be permitted to have an additional demand factor of 70% applied to the amount in 220.61B1 or portion of the amount in 220.61B2. Well, in our case, we're going to use 220.61B1. For if you look at it, it's talking about electric dryers. And it says where the maximum unbalanced load has been determined in accordance with table 220.55 for ranges or table 220.54 for dryers. So we're able to drop its additional 70%. So what do we do? So now we already took our value. We already know what our dryer, it was 36,000. We're simply going to take the 36,000 times 70%. And that's going to, or 0.70 times 0.70. And that's going to give us 25,260. That's what our neutral current is. Basically, it's 70% of the 36,000 VA. So over in the neutral column, we're going to write down 25,200. Okay, so now we have our neutral load for those dryers. Okay, we're moving on. The next thing we're going to deal with are the ranges. Remember, there's 18 of them. And they're 8 kW each, and they are 120 to 40 volt as well. So that kind of tells us we're going to have both a service value as well as a neutral value. All right, so next thing we're doing is we're just following along, going to the next one in the code, and that is 220.55. Now, 220.55 says that we can use the values that are in table 220.55. So if you go to table 220.55, you're going to see that the charging statement of the table says that column C is used in all cases except otherwise permitted in note 3. Well, note 3 is not going to apply here, okay, in this application. All right. We're going to, there's not, well, it could apply, but we compare the values between the two, you're going to see that you're better off to come out with using column C. Okay. In lieu of column C, I can use, in this case, it would be column B. However, if you do the math, then you'll find out that it's much better to use column C. So in our case, we're going to use column C. Now, if you don't know how to do this for range calculations, I will tell you this is a perfect opportunity for you to pause it, go over and watch our video on range calculations. And in the range calculations, I teach you everything that you need to know about using column A, column B, column C, when you can use column C, or when you can use A and B, when you have to use C. I cover everything. I mean, I cover every note in there, okay? In this case, trust me, column C results in a lower value, and you get to use it, okay? Now, in this case, you're coming down to the number of appliances. There's 18 of them. Then you go all the way over to the right, and it results in 33 kW. Okay, so that is going to be the value you're going to have. That's 33,000 VA. Now, just like we just did before in 220.61B1, you're going to be able to apply 70% now to this value for your neutral load. So you're going to take your 33,000 times 0.70 or 33,000 times 70%, whatever calculator you're using. That's going to result in 23,100 VA. So now you're going to write that down under your neutral column. Okay? So now I've got a service value and I've got a neutral column all the way down. Now, let's just kind of move on down the list because that's just kind of how it works. The next thing is we don't have any kitchen equipment, but 220.56, but that's dealing with other than dwelling units. So when we get into commercial applications, that would come into play. So we don't use that here. The next one is 220.60 non-coincidental loads. In this case, we are talking about the difference between the air conditioner load and the heating load. And we have to compare the two. Since the two don't come on at the same time, we only have to take the largest value of either or. Now, how do you determine which is larger? Okay, well, the first thing is first, you got to look at this air conditioning unit. Now, it's a 3 horsepower, 240 volt air conditioning unit. Okay, so you're going to determine it at 3 horsepower at 240 volts. What's the load here? So what we're going to do now is we have to go to 430.248. So let's go there because we are going to have to find out what this unit is in amperage. And it is single phase. So we're going to 430.248. I hope that's what I said a minute ago. Single phase. And at 230 for a 3 horsepower is 17 amperes. Okay, that's what the load is, 17 amps. Okay, now in our case, we already know what the amperage is here, so let's now compare that to the heat. Well, let's go and get our total load for the air conditioning and compare the two with the total load. Let's do that first. Okay, so what we had was 17 amperes. And we're going to do 17 times 240. This is for the air conditioning one. 17 times 240. Times 18. Results in 73,440 VA. So temporarily, I'm going to write that down. So that's what my VA is for the air conditioning load. Now I'm going to compare that to the heat load. And in this case, we have an actual value. It's 4,500 watts, so we don't have to convert anything. So 4,500 watts times 18 equals 81,000. Well, the 81,000 is larger than the 73,440. So we're going to take the 81,000. So we're going to write that down. So under the service column, we're going to take the heat over the air conditioning. We get to omit one of them. We take the larger. So we write down 81,000. So that goes under our service column. Now, under the neutral column, this is purely 240 volt loads. Both of them were, so there is nothing to write under that column. Okay? Now let's move on. We determined also that each one of these units obviously have to have an air handler because it has a motor, and it's what's pushing the air out, whether it's cooling or heating. So in our equation, we actually gave you a air handler value. And so in our case, the air handler was a 0.5 horsepower. So we have to do the same thing that we just did. We have to go to table 430.248. And we find a 0.5 horsepower. In this case, we use the 115 volt because that's the motor rating. But when we go back to the calculation, we're going to use the 120 because that's what the code says in part 3 that we use for calculations in 220. That's why we have to do the multiplication. So it says 9.8 amperes on a 115 volt motor. So we go back to our equation and we do 9.8. And I'm going to do this with you. If you're following along, it is 9.8, and we're going to do that times 120, because that's what the voltage is, times 18 units, and that is 21,168. So that is our air handler load that's in every unit, okay, and there's 18 of them, so that's the total. So I'm going to write down, for the air handler, 21,168. Now, since this air handler was 120 volts, we're going to have neutral load as well. And that's just going to be the exact same value. So under the neutral column, I write 21,168, and that's the value that's going under our neutral column as well. Okay, so you should have all these things adding up in your columns. Now, the next thing we have to take into account is the application of the largest motor. Now, that's a requirement in 220.50. And it tells us in 430.24 that you take the largest motor at 125%. Okay, well, we already have the largest motor in our equation here, which was the 9.8 amps, which is what we just did. So we're going to take that 9.8 times 120%, because that's what the motor is. It's 120 volt motor load here. we got the 9.8 from the 115 volt in 430.248. So I take the 9.8 times 120. Now I do it times 25% because all I'm adding really is that additional 25%. And so that equals 294 amperes. Okay. So I add that value. That's the largest motor, and I've added that value. Okay. All right. Now that's the largest motor within the equation. Now, at this point, this is where sometimes people get confused. They want to add that 25% to all motors. Now, it only says for this calculation that you apply it to one motor. Take the largest motor. Okay, so they all have motors, but you take one of the motors and do the extra 25% to it. You don't do that times 18. Okay, so that's why it's only an additional 294 VA that's added to your service calculation. Okay, don't get confused by that and try to add that additional 25% to all of the motors. Okay, you're doing a full calculation here. Okay, so you only do one motor. Now, let's add all these up at this point. So now you should have two columns. You should have a column for service, and you should have 47,700 for the general lighting and general receptacle applications. You should have 60,750 for the water heaters, for 18 of them, units. You should have 36,000 for the dryer under the service column. You should have 33,000 for the ranges. You should have 81,000 for the heat. Remember, we omitted the air conditioning. Under the air handlers, which each unit has an air handler, it was 21,168. And we took the largest motor of this whole calculation and did it at additional 25%. So the only real motor here was the air handler. So we took that air handler, 9.8 times 120 times 25%, which is 294. So I add all these up, and I should have 279,912 VA. Okay, that is my service load. Okay, and that is the actual calculated load at this point. Okay, now on the neutral side, I had 47,700. That was my general lighting and receptacle because those are 120 volt applications, so there is a neutral. I didn't have anything for the water heater. For the dryer, which were 122.40, those I had a 70% value of whatever the service VA was, which ended up being 25,200. That is 70% of 36,000. The ranges, 70% of 33,000 is 23,100, so I should have 23,100 written down. I didn't have any load for the heating for the neutral because that's all 240 volt. The air handler, which were 120, and so that value that I had under the service goes directly also under the neutral column, so that's 21,168. And of course, the largest motor application is also a 120 volt load, so that 294 VA also gets added to the neutral. If you add all the neutrals up, I have 117,462 VA. Now, at this point, we're just simply going to follow the normal calculations, VA divided by E equals I, in order to come with an amp value. So, let's do that. So for the service conductors, I have 279,912 divided by 240 equals 1,166 amperes. And that's what this service calculated load is, 1,116 amperes. Now, because of the requirements for the overcurrent devices, I have to put this on a 1,200 amp overcurrent device. Okay, if you go look at 240.6, you're going to see that the size to choose would be a 1200 ampere. Now, I also am not able to use the next size up rule here because it is over 800 amperes. So my conductors have to be sized to handle 1200 amperes. Now, I could do that. More than likely, I'm going to have to parallel that in multiple conductors in order to size that. Okay? And of course, you do that by going over to 31015B16, finding out what you need for each conductor. Easiest way is take the 1200 amps divided by 3, go over and see what you need to find a conductor, remembering that you might have conditions of use you have to account for, and we're not going to go into that here. I do have a video that I encourage you to watch called Derating Demystified that helps you understand how to do all those adjustment and corrections that you need to do in 31015 B2A and B3A. I teach you everything that you ever want to know about that in that video. So I encourage you to go watch that video. It doesn't cost anything. It's free. It's a good video, and it teaches you everything you need to know there. So you size your conductors based on the need for 1200 amperes because you're going to have it terminated into a 1200 amp overcurrent protected device. Now, what about that neutral conductor? Okay, so this is quite interesting. The neutral conductor, you typically do the same way, except for the fact that first things first, we need to come up with whatever the ampacity would be. So since we're dealing with single phase, remember our neutral load was 117,462 divided by 240 equals 489 amperes. Okay, quite a bit less than the 1,166 for the service conductors, right? So here's a couple things to remember. We have to make sure that we have a conductor that can actually handle this neutral load. But we are allowed to apply another derating value here. Okay? So this is where it gets interesting. So now, just so you understand, let's go to 220.61. Now we're dealing with the neutral now. Okay, we already did the service conductor sizes. We're dealing with the neutral. We'll talk a little bit about neutrals here. All right, so 230.61, excuse me, what did I say? 220.61. Sorry about that. It's been a long day. All right, it says these are the basic calculations for feeder in service neutral loads. Okay. Now, it goes on to say, first things first. It says the feeder in service neutral load shall be the maximum unbalance of the load determined by the article. The maximum balance load shall be the maximum net calculated load between the neutral conductor and any one ungrounded conductor. Okay? At least that size. But what we want to worry about is what's called the permitted reduction. Now, since we're dealing with the 120, 240 volt AC system, if you look in 220.61B1, let's look at 220.61b. It says a service or feeder supplying a following loads shall be permitted to have an additional demand factor of 70% applied to the amount in 220.61b1 or a portion of the amount in 220.61b2. Okay, so B1 says this. In our case, we're dealing with the application that's dealing with. It says a feeder or service supplying household ranges and wall-mounted ovens, counter-mounted cooking units, dryers, and whatnot. That is what we used in B1 in order to get our 70% when we did the actual calculations. But now, in order to get the VA. But now we're dealing with the actual load. And in order to do that, we can use B2. Now, B2 says this. That portion of the unbalanced load in excess of 200 amperes where the feeder or service is supplied from a 3-wire DC or single-phase AC system. Now, that's what we're dealing with. A single-phase AC system. So, we're allowed to apply a demand here to this value. And that demand is that 70% that we just talked about in 220.61b. So, since we had 489 amperes, we take the first 200 amperes at 100% because it says we can only apply this demand to that portion that's over 200. So, 200 is a given. So, we got to write 200 down. Now, the portion that we have above 200 is 289 amps. Now, I can take that 289 amps and now I can apply a demand factor of 70%. So, that's 289 times 70% or 0.70 depending on your calculator. That equals 202 amperes. So I add 200 and 202 amperes together, and now I have 402 amperes of calculated neutral load. That is my calculated neutral load. Okay? So that's how I come up with that, and I have to have a conductor that can at least handle this load. All right? Now, couple things let's talk about when it comes to the sizing this conductor, because I think we all know how to do this. For the service conductor, it's pretty simple. When it comes to the neutral conductor, we have some rules. We've got to have a conductor that at least has to handle the load. We have to keep that in mind. But we also have to remember that we also have to take into consideration 250.102C1. Okay, so let's go look at that for a second. Okay, so here's something to think about. Now, our equation here, we just came up with the service conductors were 1,166 amperes. Well, we have to find a conductor that can handle that. One of the things I want to kind of keep you kind of in your mind is to remember that one is you have to have a conductor that this conductor, the grounded conductor, can actually handle it. Okay? It has to be able to handle this load. But the other caveat is note 1 here of 250.102C1. And this is for the grounded conductor. If your conductors end up being larger than 1100 kc mil, okay, and even if they're in parallel, if they add up to be larger than 1100 kc mil copper or 1750 aluminum, then the grounded conductor shall have an area not less than 12.5% of that equivalent parallel set. Okay, so that's the one thing you have to remember. So yeah, it's got to handle the load, but it can't be less than 12.5% if it ends up being larger. Your parallels, the sum of them end up being larger than 1100 kc mil copper or 1750 aluminum. Okay, so you would take whatever those value is. If it was 4 of them, let's say 3 of them at 500 kc mil each, 1500, then my grounded conductor, 1, has to handle the load that we calculated, but 2, it can't be smaller than the values there because it is going to be over 1100, so it's got to be no less than, and that would be what? So that would be 1500, and let's do the math. So 1500 times 12.5%, it can be less than 187,500 kc mil, so I would have to go to Chapter 9, Table 8, and find out what conductor I would need. It can't be less than. So let's do that. Let's go on and do this. Finish this thing out. So I'm going to go down here to find a conductor. I have to have at least 187,000 for this application here. So let's see here. Chapter 9, and I'm going to go down to Table 8. And it looks to me like I'm going to need at least a 4/0. Right? So I need to have at least a 4/0. So my grounded conductor can't be less than a 4/0. All right? Now, there are, that's just a general rule. So there are other caveats to remember when you're paralleling and how you size the grounded conductor when you parallel. We're not going to go into all those because I do teach you that in another application, but you have to keep all those things into consideration when you're paralleling. Okay. In other words, I can't parallel smaller than 1/0. So if I end up paralleling my grounded conductors, I have to remember that they can't result and end up being smaller than a 1/0. But I can parallel my grounded conductors as well. So I do the same kind of thing. I determine what I need to handle the load, and then I determine how many sets I'm going to need in order to do that. So I can parallel. So, but at the end of the day, I have to take all those things into consideration. All right, but that kind of shows you how you can take the neutral conductor and apply the demands to it, which you thought would have been 489 amps. Ultimately, with the demand factors, it allows it to be 402 amperes for the total neutral load, and you size your conductors accordingly. And I just kind of threw some extra things out there to keep in mind that when you have to be 12.5%, when it exceeds 1100 or 1750, both copper or aluminum, 1100 copper, 1750 aluminum, it can't be any smaller than that. If you're paralleling because of the number of sets, remember that if you're paralleling that conductor that resulted at the 12.5%, it still can't be smaller than 1/0 based on the paralleling rules that you find in 310, and I can't remember. I think it's 310. I think it's 310.10H That's a requirement for the paralleling. So it's kind of keeping all of those things in your mind. And I didn't want to get overly complicated because really all we were trying to do here is to show you how to calculate the service conductor load and how to do the actual neutral load, or service load and neutral load. And that's really it. A couple tips to remind you at the end. If you're doing a calculation for a single family dwelling, it's really just this simple. Just don't do it. You don't have the number of units to multiply it by. You just have the one unit to multiply it. Now, you might have other things in there. You might have a dishwasher. You might have a disposal. You'll have more appliances. And you have 4 or more. You still get to apply the fixed and fastened in place appliances application in 220.53, which results in the 75% D rating or demand factor. You just don't have 18 units. You just have 1 unit. So a lot of times people really get overwhelmed by doing this, and it's really no different how you do the calculation, whether it's multifamily. You're just doing it by the number of units. Okay? So hopefully you got something out of that episode today. Hopefully I didn't confuse you too much. Again, I tried to do it in a way that it comes across in a podcast that you can follow along. But there you go. You have 18 unit condominium, 1,000 square foot floor areas, 120, 240 volt single phase application. You had a 4.5 kW water heater at 240 volts. You had a 3 horsepower air conditioner at 240 volts. You had a 4.5 kW heat at 240 volts. You had an 8 kW range at 120, 240 in each unit. 4.5 kW dryer in each unit. That's a 120, 240 volt dryer. You had the motor equation that I gave you was a 0.5 horsepower air handler, and it was a 120 volt air handler. Not sure why I did that, but I gave you it at 120 volt. I showed you how to do the service and the neutral based on all those. I even showed you how to apply the general lighting demand values in table 220.42 in order to be able to apply the lighting demand load. So really, that's everything that you need to do. If you're taking an exam, just follow it one step at a time. Remember, in part 3, you just simply, for dwelling units, just follow it down the lists as you go. Don't make it overly complicated. Follow it down. Start in 220.12, immediately jump into 220.52, then go to once you get those two together, you're in 220.42, then you're in 220.53, then you're in 220.54, then you're in 220.55, and you just follow along with the elements, and you shouldn't have any problem. As always, if you're confused or you have any questions on this basic, simple calculation, go to our website, click on the Contact Us tab, send me an email. You can email us if you want to just directly email me at info, that's INFO, at masterthenec.com. That's masterthenec.com. So it's masterthenec.com. So info at masterthenec.com. Send me an email. Visit our Twitter page. It's at masterthenec. Go to our Facebook. You can get to all these from our website. Facebook, we do a lot of questions and answer on a Facebook page. And we have a closed forum as well, so that you can ask any question you want without the worry of somebody seeing it, wondering how it's a stupid question. There are no stupid questions, my friends. We're here to answer anything we can. I try to give you the basics, especially in a podcast, because it can get very complicated. But you should be able to use this podcast and pause it and follow along. Again, thanks for taking the time to listen. Again, if you have any other questions or any other calculations you want us to do, feel free to email us, and I'll be glad to do them. So thanks again for listening. God bless. Until next time, stay safe out there.